Alright, welcome to the lecture for Wednesday, January 29th, in lieu of the lecture that was cancelled because of the weather. So let me just give you a reminder that the first test, test 1, is next week Tuesday evening from 7:30 p.m. to 9 p.m. and it will be, for our section, it will be in Williams 2215, and it will cover the material from chapters 1 through 5. We will finish the material for chapter 5 today. Okay. Okay, let's start off with a review problem. This is a problem, so that involves some masses attached to a pulley. Okay, so I have, let's say, a 2.0 kilogram mass here and a 1.0 kilogram mass. Sorry, I drew that kind of small. That says 2 kilograms and that says 1 kilogram. And it's attached to a pulley. There's no friction on the pulley. The mass of the string is negligible. And the question is, what is the acceleration? What is the acceleration of the masses? All right. Okay. Now, I actually do the problem two different ways in the notes. So let me first show you the slow way to do this problem, which is a good exercise in using Newton's second law. But then I'll show you a faster way to do the problem, which will probably be the one you prefer doing in the end. So let's first do it the slow way. That will be a good exercise. First of all, you probably can figure out quite quickly that the 2 kilogram mass is heavier, and so it will be the acceleration will actually go this way. It will go down this way. Okay. So what I will do is I will make this be the positive direction for the motion of the 2 kilogram mass. The reason I do this is it's actually going to go that way. It will make life a little bit simpler to understand. Now, the 1 kilogram mass, though, it will be, because it's attached to the 2 kilogram mass, as the 2 kilogram mass accelerates down, the 1 kilogram mass will accelerate up. And so let's take positive over for the 1 kilogram mass to be in this direction. Okay, so that's the positive convention for, in other words, if something has a positive number for its component, that means it's going down over here and it's going up over here. Okay, so now what we'll do is we will draw a free body diagram for the, let's say, the 2 kilogram mass. So we have the 2 kilogram mass, like this, and we have the tension in the string, which is going up from this string. We have the force of gravity, Fg. Okay, we know Fg. Fg is just the mass times the acceleration. So it's 2 kilograms times 9.8 meters per second squared, and that's 19.6 newtons. All right. Now, we don't know the tension, so that's kind of a pain. But what we can do is we can say that the net force on the 2 kilogram mass, so I have two different masses, so let's say the net force on the 2 kilogram mass, that will be the mass of the 2 kilogram mass, which is 2.0, times its acceleration. Okay? So A will be the magnitude of the acceleration. It will go down this way, and it will go up this way for the 1 kilogram mass. All right, just note that I have my sign conventions correct. The net force must be going down in what I'm calling the positive direction over here, and it'll be equal to the mass times the magnitude of this acceleration. Okay, so now we can solve, or we can write down an expression for the net force in terms of these forces here. The force of gravity. So remember, I'm taking this direction to be positive. So I'll have Fg minus T. All right. If you're confused, remember I'm saying for the 2 kilogram mass, I'll take this direction as positive, and then gravity will get a plus sign because it's going in that direction. It's pulling it that way. The tension is going in the opposite direction, so that's why I have a minus sign. Okay. So now I have another expression for the net force. All right. But I know what Fg is. I said that's 19.6 newtons. And to make life a little bit easier, let's drop a few units and just write things in terms of numbers. So I'll have 2.0 times A is equal to this guy. I have another expression. These guys are equal. I will have 19.6 minus T. Okay, so just to review, I did the free body diagram for the 2.0 kilogram mass. I take this direction to be positive. Okay, that's my convention. You can do something else if you'd like. And I know that I have the force of gravity going that way, and that's 2 to the mass times 9.8. That's 19.6 newtons. Then I have this unknown tension, T. So the net force will be Fg, which is 19.6 minus T. But I can also say from Newton's second law that F net is equal to the mass times the acceleration. Okay? Because A is also going in this direction, that's why there's no minus sign or anything here. So I have 2A is equal to the net force, which is also equal to Fg minus T, which is 19.6 minus T. So that's an equation I will use. Now let's go over to the other mass. So the other mass, we have a 1 kilogram mass, and we have the force of gravity due to it, upon it, and we have the tension. And I've chosen this direction to be positive. Okay, because that's actually the way the acceleration will go. So now I will do the same thing. I know this is my tension. It will be the same tension. The tension is the same on both of these guys. All right, and that's a consequence of the fact that the pulley has no mass, or negligible mass, and the string has negligible mass, and there's no friction, so the tension will just remain the same on both sides of the pulley. Okay, so in this case we know that the net force on the 1 kilogram mass will be equal to T. In this case, T is going in the positive direction, so it's T minus Fg. Okay, but this is Fg for the 1 kilogram mass, so we have T minus, and we have 1. Okay, so what is this equal to? The Fg is equal to mass times gravity, so it's 1.0 times 9.8. So let's just drop some units just to make it look a little bit easier. 9.8. So we'll have 9.8 here. Okay, now we also know from Newton's second law that the net force must be equal to the mass times the acceleration. Okay, so the mass is 1.0. And the acceleration will be, well, we don't know the acceleration, so that's A. All right, the acceleration is going up, though. We know the 1 kilogram mass is going up as the 2 kilogram mass goes down. So that's the positive direction. That's why I don't put a minus sign here. All right, so now I have this expression for the net force. I have this expression for the net force. I set them equal, so I have 1.0A is equal to T minus 9.8. Okay, so this is kind of a complicated problem. I have two unknowns, A and T. I want to solve for A, so I need to get rid of T somehow. And if I just stare at this thing, it seems like the easiest way to do that is we add these together, add together. If I add them together, the T's drop out. And so I'll have 2.0A plus 1.0A gives me 3.0A is equal to 19.6 minus 9.8, which is 9.8, minus T plus T, that drops out. And so we have that A is equal to 3.27 meters per second squared. Okay. Alright, so that took kind of a long time. So let me now show you a faster way to just get the acceleration. This will work perfectly. If you need to calculate the tension, we can solve for the tension. right? So if we plug in that A is equal to 3.27 here, we get 3.27, and the tension must be equal to 9.8 plus 3.27. Okay, but if we just want to get the acceleration, we can do this a little bit faster. And this is the trick. And I kind of alluded to it by the way I drew my diagram before. Okay, so we have the 2 kilogram mass over there and the 1 kilogram mass over here. What we will do is we will consider this motion, snaking around like this. Okay, I know this is not a straight line, but let's consider motion in that direction. Up on this side, down on this side. Sort of think of it as just a whole chain that's moving along, but it happens to have to go around a corner, so it goes around like this. Okay? So just think of it like a linear motion, but it has to go around a corner, so it's going like that. Like a little track on a tank track or something like that. Okay, so this is the 1 kilogram mass, and this is the 2 kilogram mass. So it's positive, it's going up on this side, just like we had before. Okay, we had that before, and it's going down on this side. Okay, but we're going to consider now both masses together as one unit. So we're going to consider the 2 kilogram and the 1 kilogram masses together. Okay, so the total mass is obviously 3 kilograms. Right. Now, having made this sort of snaking path like this, we can consider the net force on this system. Okay, because I'm considering the 1 and the 2 kilogram mass together, we don't have to worry about the tension in the string, because that's not an external force to the system. That's just a force that holds the two masses together. I'm considering this whole thing as my system. And so if I draw the free body diagram on it, I just have to consider the force of gravity due to on each of these guys. Okay? So there's a force of gravity for this guy is 1.0 times 9.8 going down like that. And the force of gravity acting on this guy is 2.0 times 9.8. Okay? Now here's where the trick comes in. We're now going to calculate the net force taking the snaking direction as being positive and considering both masses together. Okay, so we have this force of gravity from the 2 kilogram mass. It's going in the positive direction. It's going the way this arrow is pointing. They're pointing in the same direction. So that guy gets a positive sign. So the 2.0 times the 9.8, that's going in the positive direction. Whereas the force of gravity on this side is going opposite to the snaking direction. Okay, so we have 1.0 times 9.8 with a minus sign. So that will be the net force, the component in this sort of curved direction. And I will have 19.6 minus 9.8, that gives me 9.8 newtons. Okay, so now we can just simply use Newton's second law, that the net force is equal to the mass times acceleration. But in this case, the mass is 3.0 kilograms times A. Okay, oops. Times A. So we have 9.8 is equal to 3.0 kilograms times A. So A is equal to 9.8 divided by 3.0. And that's equal to 3.27 meters per second squared. Okay, so you can get this very quickly by simply saying we take this snaking direction like this. Right, that's just, if you're trying to figure out which way I've drawn this, it's just the way the actual system is going to go. It's going to go like that. Okay. And the force of gravity for the bigger mass will be in the positive direction because it's going the same way that this arrow is going. Whereas the force of gravity on the smaller mass is going in the opposite direction. So you just subtract the two gravity forces. So that's the trick. You just subtract the two gravity forces. That gives you the net force in this direction. And then you divide by the sum of the masses. So you subtract the two gravity forces, divide by the sum of the masses, and that gives you the acceleration, and that's actually very quick. Okay? If you have any questions on the lecture, feel free to email me. I know I obviously can't take questions right now. I'm trying to anticipate the questions as I go along, but if you have a question, just send me an email. All right, now that's it for the review problem. We will now go back to talking about circular motion. Okay. And think about the application of Newton's second law to circular motion. So let's consider our circular motion. We have some object here going around the circle this way. Okay, going this way. And so we have some velocity that will be tangent to the circle, like that. And then we will have, let's say, this is the center of the circle, and we said, let's say that the radius is r. We learned last time that the acceleration is pointing radially inward like this. Okay, that's the way the acceleration goes, and the acceleration is given by magnitude is v squared over r. In fact, we derived it last time. And remember, this was what was called centripetal acceleration. All right? So without this acceleration, just think about the ball on the string that it was spinning around last time. If there was not the tension on the string as I was spinning the ball around, the ball would just go in a straight line. It would not have the circular orbit, the circular motion. So the centripetal acceleration is the acceleration needed to keep the particle or the object going around in a circle. Okay? Now, in order to have this acceleration, remember there is this very simple relationship that the net force must be equal to the mass times the acceleration. So now what we're saying is, to have an object go around a circle, there must be this acceleration. And so it follows that there must be a net force. And so it's pretty straightforward to derive that the net force has a magnitude that's equal to the mass times the acceleration magnitude, which is mass times v squared over r. So that is the net force on a particle moving in a circle with uniform circular motion. Maybe I should have written that on top. Uniform circular motion. Now, it's important to clarify that this is not some extra force. This is not something that just appears out of nowhere. It's just the net force. Something has to provide this force in order for this particle to go around the circle. So when I was flipping, when I was rotating the ball on the string, and the ball was going around like this, okay, the string was providing that centripetal force. It was the inward tension, the inward pointing tension of the string that was providing this centripetal force. Okay, so this is what's called centripetal force, but it's not. Don't think of it as some extra force. It just needs to be the net force. The sum of all the forces has to have this property that's mv squared over r pointing inwards. Okay, so maybe I should also draw that. So the force has to be pointing inwards. So this has to be the force, and F net must be pointing inwards like that. Okay. So that's pretty straightforward, I think. And so let me just remind you of the ball and the string. So let me draw sort of a perspective on this. We have, this is the center of the circle, and this, let's say, is the ball. And suppose it's going in this direction. Okay. This is supposed to be a circular orbit. It looks a little bit funny because I'm drawing it at a slant like that. So the ball is going around the circle that way, but there's going to be an inward pointing force, F net, going like that, and F net will be provided by the string, so that will just be the tension in the string if you call it capital T. Okay. Now, the force can be provided by other things as well. So you can consider, for example, let's consider a car going around a curve. Okay, so let me, let's see, let's do a new sheet. So this will be what's called an unbanked curve. Unbanked curve. Okay, it's just flat curve for cars. So this is kind of appropriate since it snowed today. You want to think about your car making a turn. So let's suppose the car's here is a circle drawn as a perspective. You know, this it's a circle, but then I'm drawing it at a perspective like this. That's why it looks like that. And let's say this is an actual circular road. And we have the car, let's say it's going around the curve. Let's say it's going this way. That's V. And if this is the center of the circle, then there must be some net force that is going inwards towards the center of the circle. Okay? Now, this is what I'm calling just a flat curve. So this is a flat, horizontal circle or curve. Okay? Nothing with banking of the curve or anything like that. Now, the question you might ask is, what is providing this net force? Okay, if the car is really going around the circle, there must be some force that's providing this net force. So let me draw it from a different perspective. So let's draw the front of the car here, put some headlights in. Let's see, this is our little car. Tires here. Okay, and here's the road, and the tires are on the road. Suppose it's suppose here now is way over here is the center of the circle. Okay, then let's consider all the forces. Okay, so the car is coming straight out at you. Hopefully I drew this clear enough that it's clear this is the front of the car. So the car is coming straight out at you. That's the velocity of the car. It needs to make a circle, so it's going around like this. Okay. Let's think about the forces acting on this car. So we have the force of gravity going straight down like this. We have the force, the normal force, which will balance the force of gravity going up like that. Now, the force that will actually provide this centripetal force, this net force pointing towards the center of the circle, will actually be the force of friction. Now, it's the force of static friction that provides this inward pointing, this net force that points towards the center of the circle. It's static friction because the tires are not sliding. Tires are not sliding. Okay, they are rolling, but that's not the same as sliding. The point is, when something rolls, the contact point with the ground is not sliding. The sliding is doing this, but the tires are just simply rolling. So there's no, in particular, there's no sideways motion of the tires at all, which is the important thing here. So it's the force of static friction. So the static friction force is what's providing the net force, that is the centripetal force. So we simply have that the static friction force, Fs, is going to be equal to the net force, which must be this mv squared over r. You might ask, what about the normal force and the force of gravity? Well, they just cancel each other out. Those are just two vertical forces that must balance out because there's no motion in the vertical direction. There's only a motion in the horizontal direction. Okay? So that's actually pretty straightforward. The static force provides the net force, which is this mv squared over r. Okay. Now, if the tires are skidding, then that's not a good situation. Then we will have to have, we won't have static friction providing this force, but instead we will have kinetic friction provides the force, then kinetic friction. Right? And in that case, if it's going around in a circle, then we can say that Fk is equal to the net force, which is equal to mv squared over r. Right? Now, however, this case is kind of when your car is out of control. You don't want to be in this situation where you're going around a curve and then you're sliding out. That's no good. It won't be going in a nice circle anymore. Now, the typical problem you might get with these types of flat curves is they might ask, what is the required coefficient of static friction, mu sub s, to enable the car to go around a curve with a certain radius r with a given speed? And you just use the fact that the maximum static friction force is equal to mu s times the normal force, which is just the force of gravity, okay, because they're balanced out. And so you just put these together. Your maximum static friction force, this is the maximum centrifugal force, centripetal force you can get. And so you just set these two guys equal to each other and solve for mu sub s, or if they ask for the speed, you can solve for v, or if they ask for r, you can solve for r by putting these two together. Okay? Now there is a slightly more complicated problem that I will try to explain, which is actually used in race car tracks. So these are banked curves. And the idea of the banked curve is to allow the car to go around a curve much more quickly by using a tilting of the road. And so let me show you a banked curve with no friction. So let's just make life easy. The case with no friction. And you can make some very complicated problems where you have friction and a banked curve, if you like. So let me show you. So the basic idea is we have like a bowl, right? And the car is going around a curve like this that has some banking to it, just like in a car racing around the curves. That they bank the curve so that that helps the car go around the circle. It gives you more. It helps you out with the centripetal force. Okay, so let me try to explain what's going on here. What we have is we have the banking. So let me draw a perspective where the car is coming straight out at you like this. Okay, the car is coming at you like this. We have a banked curve. Here's horizontal, but this is the surface, the inclined plane, if you want, that the car is on. And so the car is over here. Here's the front of the car. Okay. And here is going to be the center of the circle. Okay, here's the center of the circle. Right? So the car is coming straight out at you. It's going to make this circle. Let's now analyze the forces on this. We're considering the case with no friction, so this is a little bit easier. All right, so we'll have the force of gravity. So let me just make it big and red so you can see what I'm drawing, otherwise it gets a little messy. Fg is going straight down like that. And just like we had for the inclined plane problem, we have the normal force has to go in this direction here. Fn. Okay, now here's where the banked curve problem is a little different from the inclined plane problem. For the banked curve problem, the motion is actually in the horizontal direction. It's not we're not concerned about sliding up and down the plane in the bent curve problem. We're just having horizontal motion going around a circle. And so we're going to actually consider the components of the force in the horizontal and in the vertical directions. Okay? So even though there's an inclined plane, this is a slightly different problem where we consider the components in the horizontal and vertical components. The reason, once again, is because the motion is in a horizontal circle. It's going around a circle that's horizontal. It's going around like this, okay, where this is the radius. Alright, so we'll consider horizontal and vertical components. Okay, so first of all, let's consider the vertical component. Vertical component. For the vertical component, so we're just looking in this direction, so let's take this to be positive, vertical direction. Okay. So the vertical components, we have F net, this will be y, the y direction. Okay, F net in the y direction. Okay, in my notes let's not put it up there. F net in the y direction is the force of the normal force. Okay, so we have this angle here. It's the same angle as this angle here. So we need the component of Fn in the vertical direction. So that will be Fn times, well, we have this little triangle. This component here will be Fn times the cosine of the angle. That's positive, it's going up like this. And we have the force of gravity going down, so that's minus Fg. Okay, but we know that the net force must be equal to 0 because it's not flying off or tunneling down into the bent curve. So we can solve for Fn. Fn is equal to, bring this to the other side, we have Fg, and then we divide by the cosine of theta. We just have Fn cosine theta is equal to Fg, and then divide by cosine theta to get Fn is equal to Fg over cosine theta. Now we know that the force of gravity is just m times g, so this is m times g divided by cosine theta. I should mention that the force of this normal force can be bigger than the actual weight of the car, because in fact it usually is, because you have cosine of theta in the denominator here. Okay. All right. Now let's consider the horizontal component. Right. Let's actually go in this direction, because that's the way the acceleration needs to go. It needs to point towards the center of the circle. Okay. So it's a little bit weird that I make the positive x coordinate go to the left, but this will be the positive horizontal. And oops, horizontal. That will be the x direction. Okay, so the horizontal component we will have, okay, this is easier. We don't have any horizontal component to the force of gravity, it just goes vertically, so there's no horizontal component at all. But this normal force has a horizontal component, and so the net force in this x direction will be this component here, which is going in what I'm calling the positive direction. Okay, so that will be Fn times the sine of theta. Okay. All right. Now, remember we're going around in a circle, so there needs to be the centripetal force, which is just the net force. There needs to be a net force equal to mv squared over r. Okay? If it wasn't that, if we didn't have that, then we would not be going around in a circle. So we have these two equations. We have Fn sine of theta is the net force in the x direction, and we also have it must be equal to mv squared over r. And let's not forget we have something for Fn as well from this equation. So let's put this all together. We have Fn is equal to the sine of theta is equal to mv squared over r. Okay. And we will have Fn is equal to mg over cosine of theta. I'm just replacing this from here. And then we have the sine of theta is equal to mv squared over r. Okay. And we can cancel stuff. We'll cancel the n's. We have g sine theta over cosine theta is equal to v squared over r. And then this guy is just the tangent of theta. Tangent of theta. And let's also divide by g. So we'll have the tangent of theta is equal to v squared over g times r. Okay? So this is how you would relate the banking angle to the speed around which the car goes around the curve and the radius. Now this is actually useful for civil engineering in that if the road is very slippery, if you have ice on the road, you don't want to rely on the force of friction to provide the centripetal force to allow the car to go around in a circle. So what you can do is you can make a banking angle, and you can tune this banking angle such that the tangent is equal to tangent of theta is v squared over gr, where v is, you know, the speed limit or the typical speed of the car going around this curve, and r is the radius of curvature of this curve, just basically the approximate circle that the car is going around. And you solve for theta, and then you can bank the road that way, and that will help the cars go around without needing to have any friction. Now, if you made the banking angle steeper than that, then the car can go around the curve, but what will tend to happen is it will tend to want to slide down the curve. So if you made it too steep, then that's not so great either. Okay. Now let's do an example. So once again, if you have questions on this, I know the banked curve problem is a bit complicated. It's one of the more difficult problems we're doing in the course, but hopefully that was pretty straightforward to understand. But email me if you have questions on that. All right, let's do an example. So let's consider that a roller coaster makes a roller coaster makes a vertical circle of radius 20 meters. Okay? So the question is, what is the minimum speed so that people don't fall out, that people and possessions, I guess it's important that you don't lose your purse or your cell phone or something, so that people and their possessions don't fall at the top of the circle when upside down. Okay, so we have this roller coaster that has some circle to it. It does, it does something like this. It goes around and it comes like that. Okay, and so we have. Let's draw a little cart of the roller coaster. Okay, and then there's some person here enjoying themselves in the roller coaster. And the roller coaster, let's say it's going around in this direction. Okay. Now you can ask things like forces acting on a person in the roller coaster. Okay. Now that can be a little bit complicated because you might have the seat belt on the person. So let's actually consider an object that the person is just holding with their fingers, so that they're not actually trying to hold on to something. So if they're not really trying to hold on to the let's say the cell phone, then the only force that will be acting upon it will be the force of gravity. So there's a force of gravity that's going down Fg like that. Now, if you want it such that the object doesn't fall down, okay, what you need to do is you need to have the roller coaster go fast enough so that the force of gravity provides exactly the centripetal force needed to keep the cell phone going around in a circle together with the roller coaster. So in other words, you have a cell phone, you just have it, you have your cell phone in your hand, you're going around the roller coaster, and what you want is you want that cell phone to go around with you, okay? And in order for that to happen, you need for the force of gravity acting upon this cell phone to provide the centripetal force for going around the circle with this given speed v and radius r. Okay? If you were to go faster than that required force, then that would also be okay, because what would happen is the cell phone would actually try to go up this way. Okay? It will. If you go faster than that required speed, then you won't lose it. The cell phone won't fall down it, but it will actually kind of go up. Okay? All right. So let's solve for that. We know that r is equal to 20 meters. Okay, we need the net force. Okay, we know that the net force is just mv squared over r. That's automatic. That you should know that. Just get used to that. And we know that the net force is being provided by gravity. We just said that. mg. So we just set these two guys equal to each other. mv squared over r is equal to mg. And then we can cancel the m's. And we have v squared is equal to g times r. And v is equal to square root of g times r. And now we can solve square root of 9.8 times 2.0 is the radius. And so that comes about to 14 meters per second. Okay, now let's talk about something, a little wrinkle on top of uniform circular motion. So if you have questions on this again, please email me. Now, the next thing we'll talk about is non-uniform circular motion. Non-uniform circular motion. So this is the case where the speed going around the circle is not constant. So the speed going around circle is not constant. So instead of going like this, we have maybe some acceleration, so it's going faster, or we have it was going around and it's slowing down. Okay? So in this case, we have a little wrinkle to it. Now, in this case, if we have our circle like this, and we have some radius r like that, then suppose we know that the speed, so this is speed v of t, it's a function of t. Okay? So we know that if something were actually just going in a straight line and its velocity was changing, then the velocity is changing would give us an acceleration. For example, it was speeding up. We know we'd have an acceleration going in that direction. And so the same thing happens here. And there's going to be some component of the acceleration that will go in this direction. Let's say it's speeding up, so then it would actually go in this direction, and this will be what's called a tangential, just the tangent component. Okay, but it's also still going around in a circle, and so we still have what we said before, this centripetal acceleration, which will, in this case, we'll just call a radial to keep it straight. Which one is which? Okay. So for uniform circular motion, v of t is just a constant function. There's no a tangential because the speed just remains the same, and we only have this radial. But when we have non-uniform circular motion, we have tangential, a tangential, and we have a radial. And the formulas are actually the same formulas we already know. For the tangential, it's just like we had for a motion in a straight line. You just take the derivative, the time derivative of the speed. Okay, that makes sense. That's the sort of formula we have if something's just going in a straight line and it's speeding up, then we have an acceleration going in that direction. If it's slowing down, then we have acceleration going in the opposite direction. Okay, but we also have the radial acceleration, or the centripetal acceleration. That's just v squared over r. Okay, I put in the explicit dependence on t to remind you it depends on t, but it's just the same formula, v squared over r. So you have both of these components. So if you have a question like on the homework where you're trying to figure out which way does the acceleration vector go, then you just have these two components. You have a component of the tangential, you have a component of the radial. If you have both and you add the two vectors together, for example, in this case it looks like it will go kind of in this direction. Okay? Alright, if you have questions on that, just please email me. The last thing we'll do in today's lecture is to do just a simple review problem to get you ready for the first midterm. Let me just remind you once again that we have that I've put up 4 practice tests on the Moodle page, so please go there and start working on that. We've already covered all of the material covered all the material up to chapter 5, which is what's being covered in the test. And so you should be able to do all the problems in the review material. Let's do one review problem. So let's suppose we have y here, and I have x, and I have an angle of 30 degrees, and this force F1 has a magnitude of 100 newtons, and we have another angle here, same length, and 45 degrees like that, and this is F2, and that's 100 newtons. And the question will be, find the magnitude of F1 plus F2. Okay, and the alright, let's just do this as a pretend clicker, even though this is just a YouTube video. Why don't you, I give you some choices, 13 newtons, 26 newtons, 53 newtons, and 74 newtons. So my suggestion is to pause the video right now and try this yourself, and then once you get an answer, go ahead and take a look at the solution. Okay, so go ahead, pause the video. Alright, now let's go through the solution. Let's do the x components first. So remember, we can't just add the magnitudes together, we have to add the components of the vectors together. So F1 in the x direction, okay? So we have our little right triangle. Remember, the vector must be the hypotenuse of the triangle. And so we have, this will be the x component. So we will have 100, let's drop the newtons just to make life easy, 100 times the cosine of 30, because that's the adjacent side to this angle. And so we have 86.6. Okay, and then F2 in the x direction. So that's this triangle, and we want this component. So that will be, alright, so I'm going to work with this angle 45 degrees, but then I have to remember that the component is actually going in the opposite direction, in the negative direction. So I'm going to have a negative sign in front, okay? If you want, you can actually do all of this together by saying the angle is going to be 180 degrees plus 45, which is 225. But if you're like me, you like to think of angles smaller than 90 degrees, so you'll get this component and then put the minus sign in. So this will be 100 times the cosine of 45 degrees, which is negative 70.7 newtons. Okay, so then the total x component will be 86.6 minus 70.7, which is 15.9 newtons. Okay, now we can do the y components. So now we're looking at this guy. We have F1y. That will be 100 times the sine of 30 degrees, which is going to give me 50. Well, I'm not going to drop the units until the end. And then F2y will be, okay, once again, I'm going to get this side here, but I'm going to remember that it's going in the negative direction, so there's a minus sign, so that'll be 100 times the sine of 45 degrees. Oops, we don't need this. And that gives me negative 70.7 again. And then the total in the y component will be 50 minus 70.7, which is minus 20.7 newtons. Okay, so we have the vector F1 plus F2, or I gave it a name, F total. That will be 15.9 newtons. Oops, that's supposed to be decimal, comma, minus 20.7 newtons. And then the magnitude of the total force will be the square root of the sum of the squares. So 15.9 squared plus 20.7 squared newtons. And so that comes out to 26.1 newtons. Okay. So if you have any questions on this lecture, please let me know. Otherwise, I'll see you all in class on Friday.